visited last week. He'll be visiting again visiting this week, and then we're hoping maybe he'll come back later in May. So his stay ended up having to be cut short, but we're some exciting news on Mission in a minute. So Ryan got his PhD at UC Berkeley under Alex Filipinko in 2008, and that's when I first met Ryan. He went on to be a Clay Fellow at CFA, and then a professor at Illinois, where he's been since 2013. Among other things, he's worked on a lot of things with exploding stars. Probably what he's best known for maybe is making the term 1AXs, so a subclass of 1As, which I must admit was probably met with a lot of healthy skepticism by the community, because people always want to make these new terms, and we have so much, so many terms in our community. Like, what's another one? But I think he's been vindicated somewhat, as we've seen during our tea this morning. We've probably made more progress on 1AXs in the last couple years than we've made on understanding progenitors of 1As in decades, in some senses. So Ryan's received a number of awards, including becoming a Sloan Research Fellow in 2015, getting the very distinguished Scialog Fellow in 2015 by the Research Corporation of Science Advancement. And then most recently, his team was selected as a science investigation team for WFIRST, which is one of the reasons why his stay now is being cut short. But it gives him something exciting to tell us about today in his talk. So take away, Ryan.
All right, thanks, Tony. That was a great introduction, a little embarrassing. It is great to be here. Thank you for making this happen. And Juna, I know she has a slightly longer commute than normal, but I guess she couldn't make it. But thanks to her and thanks to all of you. And so first of all, I look back. This is the 5th talk I've given here in the last 7 years. So this is really kind of my home away from home. And so it's good to see so many friendly faces. And it's particularly nice being here in January. I just checked the weather in Champaign. This is accurate as of a few minutes ago. It feels like -4. Better. Okay, so today I'm going to talk about supernova cosmology, which is definitely different from all the 1AX and 1A physics that I work on. And so it's also a little interesting and daunting to give this talk here, because I even titled it Continuing the Legacy of Supernova Cosmology. And much of that legacy was built either here or other parts of Carnegie down in La Serena. And so hopefully I can do some justice to that, but apologies in advance already. And so I also wanted to point out that as I'm traveling around this semester, I'm on sabbatical, so I'm going to be spending some time in California at different places. We talked, and this is mainly for Barry, who kept calling me a transient, who works on transients. I found this a little while ago. I work on a different kind of transient, although this is perhaps a little more apt because this next few months I'll be in California. Okay, so now on to the science. And so first, just my very simple slide on type 1a supernovae. I think this encompasses everything that you need to know for this talk, that they come from white dwarfs, they're in binary systems, they accrete some amount of material from their binary companion. It doesn't have to look like this. It could be another white dwarf. That doesn't matter for this talk. Eventually, they explode, and they're very luminous. I'll also give this very, very simple explanation of standard candles and how you can measure distances, which feels like the silliest thing ever here. But in case you weren't aware, if you have two objects that are the same luminosity but at different distances, the flux that you receive on Earth or in your telescope is going to be different. And you can then infer a distance, if you know the luminosity, by just invoking the inverse square law. Now, the great thing about this is then you can compare this to theory, where you expect some relationship between the luminosity distance and things like the redshift and cosmological parameters. And of course, I couldn't give this talk without showing this diagram where, almost a century ago now, Hubble did exactly that. He measured distances and some sort of redshift and discovered that the universe was expanding. Now, we continue that kind of progress today using type 1a supernovae, but type 1a supernovae are not standard candles. And you may have one that's a little bit brighter than another. And if they're at different distances, because of that difference in the luminosity, you could end up getting the same flux. And so you have to correct for that if you want to have a very precise distance. Now, a few decades ago, Mark Phillips, among some other people, but primarily Mark, noticed that the light curves of type 1a supernovae, how they rose and fell, they depended on the overall luminosity, such that the more luminous supernovae, they have broader light curves. It took longer to rise, longer to fade away, and the lower luminosity ones were faster. They rose quicker and faded faster. And if you can determine this decline rate, or delta M15 as Mark dubbed it, then you can infer the luminosity and get a very precise distance. And so if you just assume that a type 1a supernova is a standard candle, and you make some sort of Hubble diagram, you can get a scatter in that Hubble diagram of something like 0.4 magnitudes, not very good. If you include that light curve information and a correction for the intervening dust, then you can get down to something like 0.18. And at this point, type 1a supernovae are exquisite tools for measuring cosmological distances, because they're incredibly precise and they're incredibly luminous. Now, back in the 90s, two groups did this. They measured a bunch of type 1a supernovae in the local universe and compared those distances to those at redshifts of about 1/2, and measured the deceleration parameter, this Q naught, the thing that goes after the Hubble parameter, and ended up finding that the deceleration parameter was negative, that the universe was accelerating. These are the first two results indicating that we are living in an accelerating universe by Rees et al. And Perlmutter et al. Back in the late 90s. And what you can see is that in this omega lambda omega matter plane, that the supernova results indicate that there's a non-zero omega lambda term, this accelerating universe that we now say is being powered by dark energy. That was the first solid evidence of that. And just a few years ago, and in fact, I was here when the announcement was made, the three people here before you, Adam Rees, Saul Perlmutter, and Brian Schmidt, received the Nobel Prize for Physics for the discovering of the accelerating universe. And this is a discovery that's similar, perhaps not exactly on par, with the discovery of the expanding universe. You know, we found a huge additional component to our universe, something unexpected, and something that really does tell us amazing, interesting, new things about the world in which we live. Now, I'll just point out this was a group effort, and this is the high-Z team, which Brian was the PI of, and Adam wrote up that first major result. But there are a number of people who were involved, and this is the entire team when they were at the Nobel ceremony. And I'll just point out a few people. So first, I should definitely point out Mark Phillips in the back. So let's see here. Who else should I point out? My advisor, Alex Filipinko. I was a postdoc at Harvard where I worked a lot with Bob Kirshner and Chris Stubbs. I'm sure many of you people know the other people who spend a lot of time in Chile, like Chris Smith. Nick Sunsef, who used to spend a lot of time in Chile and now not as much. So this was a great achievement a couple of decades ago, but you know, we're in a new millennium now, and we've done a lot better since then. So here's sort of state of the art as of today. We now have a Hubble diagram. Those first Hubble diagrams included about 50 supernovae. We're now about 1,000 supernovae. Here's some compilation of different groups. There are these high redshift surveys, like Sloan, Pan-STARRS, SNLS, and then the Hubble surveys at the very highest redshifts. And then there are the nearby surveys. There's CSP, of course, done by people here, the CFA groups, which are all these other surveys. And it's the differential measurement that matters. We don't actually care how luminous type 1a supernovae are. We just say how bright is this one at redshift 0 relative to this one at redshift of 1/2. And so it's always critical to remember that you can't just measure high redshift supernovae, you can't just measure low redshift supernovae, you have to do the whole thing to measure cosmological parameters. So with those data, or at least something similar, I just want to visualize how far we've come. This is the original plot from Adam's paper. This is a recent plot that came out from the JLA collaboration that I'm a part of. And the supernovae here are in blue. The C and B is in green. And it's worth, just sort of staring at that and seeing we really have gone a long way, especially when you notice that the combined contours are that little bit there. That's how well we know these parameters. And we can zoom in on that and say this really is sort of where we are today. That dark energy takes up something like 70% of the universe, and really primarily dark matter is something like 30%. And so this is an old plot. It's not exactly accurate based on current constraints, but something like 75% of the universe is dark energy. And we know almost nothing about it. Now, the thing that I tell people in public talks is there's a very similar situation. Our universe, our world is covered with water, about 75% of it. So imagine if you knew that water existed, but you didn't know anything about it. Maybe you knew it was wet, but that was it. That's sort of the state that we're at. And so we really are left with this question of what is dark energy? And I'm sure many of you have seen this where we think about it in terms of this equation of state parameter W. You don't need to think too much about that for this talk, but realize that this is sort of our first best way of getting at it. And there are many other ways. This also assumes that GR is correct, and it doesn't have to be. One of the explanations for the observations could be modified gravity. We're right now, for the purposes of this talk, just doing the very easiest thing. Now, I put up a few points, and I'll mention, although I'm sure everybody already knows, that W of -1 is what you expect for a cosmological constant. And the observations right now are consistent with that to about 5% in W. And so you might say it's time to throw things up, and why waste any more time on that? And I'll just quickly say that there are currently, and there might be more in the future, several problems with the cosmological constant. The first one is just if you go from the basic theory and you say, what should the cosmological constant be if you just take the Planck scaling, it's 120, or if you invoke this string theory manipulation, it's 60 orders of magnitude too small. So there has to be some sort of explanation for why this lambda is so tiny. Another question is, why is omega lambda about the same size of omega matter? That's related to this first point, but not exactly the same thing. Because it could have been still 10 orders of magnitude off and be significantly larger than omega matter. And then finally, it's always worth some perspective. And what I can say is that there was a very early epoch of accelerating expansion, inflation. And if you talk to physicists back at 10 to the minus 32 seconds, they would say, this looks a lot like a cosmological constant. But then that acceleration stopped. It wasn't the cosmological constant. So if you're a Bayesian, you'll say, based on the one data point that we have, you might move away from this idea of cosmological constant. So I'll point out, first of all, that this is a great way of looking at the nature of dark energy. But if you're interested in just sort of the expansion of the universe, you might want to take a kinematic approach. And we can do that as well, where essentially instead of looking at things like W, you can go back to this idea of looking at Q0, the deceleration parameter, and go further on from there and build up this kinematic universe and then compare that to models. And of course, so after acceleration, if you take the derivative of acceleration, who knows what that's called? Right. It's the jerk. OK. So in this paper, that Adam wrote a few years ago that I was a part of, there was some evidence that there might be a jerk. And so in the New York Times, this was the headline. But then, this was the picture. I thought that it was appropriate for this audience. Okay, so like I said, if we are focusing on W, I think we should have a little context here. This is the difference in your distance modulus, your difference in magnitudes for different cosmological models. And here's a 10% variance on W relative to lambda CDM. It's worth pointing out that this is what was measured back in the 90s, this difference that was resulted in a Nobel Prize. And we're trying to do something exceedingly difficult compared to that. But we've already, I made this, I think, for my thesis, and we're well beyond this 10% idea. This is the current state for W. The supernovae, again, are in blue. And the combined results between supernovae and CMB, and I think BAO is excluded for this, is just this gray circle here, where we know W to about 5%. And so again, you might say this looks, and of course, this is the cosmological constant at -1, and you might say immediately that this is enough, we should stop. We don't want to just get that, second, third, fourth point beyond a digit beyond the decimal point. But if I show this slightly different characterization of dark energy, where you have the potential for evolving dark energy, something where you measure W now and then W sometime, or something similar to the derivative of W, you'll see that things blow up significantly. This one little point here is going to be your cosmological constant. And you can see even when you open this up, W naught, W today, goes from maybe -1.1 all the way out to -0.9. Is significantly bigger just in that one parameter when you allow this expansion. Now, from the point of view of supernovae are great at measuring these particular parameters, and particularly good at measuring W naught, the dark energy constraints today, because they have the best constraints in the local universe. Below redshift of about 0.5, no other cosmological probe can have the same kind of sensitivity as supernovae. BAO, the volume is just too small. Weak lensing, the volume isn't particularly good either. This, we can get a supernova every second if we really tried, and we could just continue to pile things up. The problem is we're no longer statistics limited, and this is one of the best ways to show this. These are some slightly earlier constraints, where the blue contours here are the supernovae again. But this is where they are only statistical uncertainties, and then if I show the systematic uncertainties included, they balloon up. And it turns out now that as of today, the systematics are larger than the statistics. That means that you can measure as many supernovae as you want, but you've hit this floor, it's going to be difficult to get any better constraints. So the name of the game going forward is addressing these systematics. And the way to do this, if you're an efficient person, is to figure out your systematic error budget, determine what the largest error piece is, and then pound away at that. And so we've done this. This is a recent error budget for the pan-stars analysis. And you can see that the systematic uncertainty is larger than the statistical uncertainty. And then these are the individual components for that systematic uncertainty. And by far, the largest component is the photometric calibration. And it's not just the photometric calibration generally. It turns out that all of the high redshift supernova programs have reasonably calibrated photometric systems. The problem is actually with the low redshift samples. And part of the problem is we have so many different systems at low redshift that have been taken since the late 80s. Some of these systems were supernovae were discovered on photometric plates and then followed up with CCDs, small format CCDs. The images no longer exist. There's just some photometry and some AppJ pictures of finding charts. So you can't re-extract any photometry, and some of these cameras no longer exist. Some of the filters no longer exist. Some of the telescopes no longer exist. So there's no way to recalibrate that data either. In fact, this compilation of different surveys that make this low redshift sample, there's 8 different low Z samples that go in. This is just sort of taking up these different pieces. Like this JRK07 actually has something like 5 subsamples. And then if you say, all right, these are just samples, these are groups of people who are doing things, and really what you care about are the photometric systems, then you have more than 13 different systems. So maybe you had one telescope, but then you changed the camera. And with that camera, you have a different CCD. So that has a different calibration. At some point, your filter breaks. You have to get a new filter. That's a new system. So this is very complicated. And it directly affects our measurement of these cosmological constants, or cosmological parameters. And again, a good way to show this is we did this analysis with the Pan-STARRS data where we excluded different low Z samples. So you can read all the numbers, but I'll just point out for excluding a couple of these samples, including the Carnegie sample, if you excluded, say, this JRK sample, W would shift by 0.02 in one direction, and if you excluded the CSP data, W would shift by 0.02 in the opposite direction. So that's not the whole story, of course. That's a part of it. The real calibration error is closer to 0.04, but that's just an indication of the real difference that can happen by including or excluding individual samples. So about a year ago, I came to the conclusion that we really need to address this problem. You can't just get more supernovae to figure things out. You can't even do things with high redshift data. Part of DES. DES isn't going to be able to make any traction on this until we address this at low redshift. And so what I said was some of these things are just, the supernovae are too old. The data are too bad. There's no way to really deal with them. We should just get rid of a lot of it and replace it with something else. Now, luckily, yeah, sure.
Are the coherent flows contributions that small at low redshift?
So by low redshift, I typically mean between redshift of 0.015, 0.02, and 0.1. Okay. So at that point, yeah, it's not so bad. And so, all right, maybe I'll take this time. For all these samples, they have large numbers of objects, but then we have to cut them down for our cosmological analyses. And one major reason we cut them is that they're not out in the Hubble flow. And so, you can see, Carnegie does well, but almost half their sample is removed, and a lot of it is because they're too nearby.
So you cut until you get coherent flows out of the...
Well, we make corrections for coherent flows, but we also say that there is some point where they're just too uncertain. Okay. All right, so to address this problem, we are lucky that we are now in really a golden age of transient astronomy that's going to continue on for at least a decade. Here's just the number of supernovae discovered and announced as a function of time, going all the way back to 1885A. And you can see that this is a logarithmic plot, that things have really changed over the last couple of decades. And there's some obvious events, right? So this is sort of Zwicky. And then there was, right around, what year is that? In 1987, there was something that happened that all of a sudden things picked up. Somewhere in here also there was, a lot more CCDs. And then right around here, maybe that had something to do with the dark energy stuff. And then, just recently these giant surveys like Pan-STARRS and PTF. Last year, there were more than 3,000 supernovae discovered. That's more than all the supernovae discovered between beginning of time and 2005. Okay, so in 1 year. And that's announced, right? So for instance, PTF really doesn't announce their discoveries. So the number might be twice as much. Okay, but going forward, there's this thing looming on the horizon. And LSST will soon discover something like 100,000 to 1 million supernovae every year. So when I say golden age of transient astronomy, it really is. If you're not doing something in the time domain now, there's a good chance you will be in a decade.
Do you ever imagine getting the systematics down to where it matters that they got a million here?
Well, so I'll get into this, but one way that you can address systematics is through larger numbers, right? So you can slice and dice your sample and try to determine what the physics is that way, or you could find a subsample that's particularly precise and doesn't have as many, so say you think that dust is the biggest problem. So you only want to look at things in ellipticals. You could do that. If you have a million objects, then you can get plenty of statistics. So those are the sorts of games. Okay, so we're using this possibility that we are just finding orders of magnitude more objects than we were a few years ago to address the fact that we have to rebuild this low redshift sample. And I just have a few things for what I think the ideal low redshift sample is. I say single system for one, if you just want one system. You want a really good ruler that's well calibrated, and you want one of those. You can, of course, combine with other rulers if they're also well calibrated. But for me, myself, if I'm just doing my survey, I just want that one. Now, ideally, you would want full sky coverage with multiple observations. And that's because for every image that you take, you have some sort of 0 point. And if your images overlap, and you have stars that overlap, what you do is you have to do some sort of chi-square minimization of every image, every 0 point, to make it so that all the stars match up. Right? So this is what's called Uber calibration. It's been done with Sloan. It's been done with pan-stars. And the more observations you have and the more overlapping stars you have, the better you do at that. And you might have a million parameters to fit for, but that's not a problem at all. You want precisely measured filters. We do this with, say, pan-stars. We do this with a tunable laser that we have on site. We step through in 10 angstrom bins, figure out the full throughput of our system, including the filters, the CCDs, the optics, everything. And you want to do that regularly so you can see how it evolves with time. Ideally, you want an existing data reduction pipeline, something that you know works and doesn't have any weird aspects or systematics involved. And then if I'm getting greedy, I'll say I want a large high redshift sample on the exact same system so that you can make a single measurement of cosmological parameters, doing that differential measurement with one system. So you have no cross-system systematics. If you put all these together, there's exactly one thing that can do this. There could have been one earlier. You could have done this with Sloan, but now the camera is in the Smithsonian. So that's not available. There's exactly one system that's available right now, and that's pan-stars. So for the uninitiated, pan-stars is a roughly 2-meter telescope with a 7 square degree field of view. I think it still has the largest entendu of any telescope, although Subaru plus Hyper Supreme Cam might have beaten it. It does definitely have the largest camera in the world, a 1.4 gigapixel camera. And it had a supernova survey for 4.5 years, and it took 25% of the time for the supernova survey. And what happened, here's sort of the cumulative and individual night observations of pan-stars. This is RA and DEC. And this is the sun and moon. What it did is it took a bunch of images all over the sky, but it also focused in on these individual fields. Those are the supernova fields. There were 10 of them. It imaged them every night that they were up in some filter. And after 4.5 years, we have a spectroscopic sample of something like 400 high redshift supernovae, type 1a supernovae, and we have a photometric sample, things where we didn't get spectra of the supernovae, but we can get spectra, and we are getting spectra of the galaxies, of something like 3,500 or 4,000 supernovae, very large. So this is the current in prep version of the pan-stars Hubble diagram with those roughly 400 supernovae at high redshift. And you'll notice that we are still using this combination of different surveys at the low redshift. But what we want to do is replace this with a pan-stars sample. So together with Armin Rest and Dan Skolnick, we started a survey called the Foundation Survey, and we called ourselves the Founding Fathers. There are a lot of great jokes you can make. If anybody's a sci-fi fan, of the Foundation series, and right. So there are a lot of good jokes. Anyway, the idea here is to use the pan-stars telescope with a 7 square degree field of view and observe one supernova at a time. And the reason for that is to get the calibration, the biggest systematic. So we're measuring one supernova at a time with the world's largest camera because it's also the world's best calibrated camera. And we're doing this in an ad hoc way where other surveys like Assassin are discovering supernovae and then we're following them up. And we're trying to optimize this so that we can find sort of 408 to 800 supernovae at low redshift in the next few years. And then we'll have a combined sample with the high redshift sample of around 1,000 supernovae on a single system. Here are some predictions of what might happen by the end of this, where we start with just sort of the current pan-stars analysis in red, and then we add in more objects at high redshift, and we add in these new objects at low redshift. What you might not be able to tell by eye is that in terms of precision, this is like a 2.5 time improvement, which would be exceptional. In fact, there hasn't been a jump that large in the last decade for supernova cosmology. So it's something to consider. This is our strategy. Others typically discover them, although we've been running things through a Supernova Survey through pan-stars as well, and we find more supernovae now than any other survey, but a lot of them are at too high of a redshift. We find things in the Hubble flow. That's what we typically follow up, although we are also following things up at low redshift, very low distances where we can get absolute distances using other calibrators to those galaxies. That'll be useful for the Hubble constant. We want things with low Milky Way reddening. There are enough supernovae we can pick and choose. There's no reason to worry about the Milky Way dust. And the key is that we want at least one pre-maximum epoch so that we can very precisely constrain that peak brightness. We've determined that if you have 7 GRIZ epochs, you get distances where the internal scatter of the supernovae are going to be larger than your photometric errors, and that's the floor that you want to reach. For these very nearby things, we're also getting wideband observations, and we're getting nightly observations instead of just 7 epochs. Our idea was with this, you get a statistical uncertainty that's less than the intrinsic scatter. That means that you don't win by getting more data unless you want to study physics, and that's not the primary purpose of this survey. And we started in April. Okay, we've been getting data. This is what one of our images looks like. This is what one of our light curves looks like, although this only has 6 data points and most of them have 7. We already have 82 supernovae. We started in April. That already makes us the second largest sample at low redshift. We have about 40 nights on 4-meter telescopes. I'm the PI of this program. Over 2 years to follow them up, make sure that they're 1As, determine spectral properties, get good redshifts, those sorts of things. We also are collaborating with Saurabh Jha and Bob Kirshner, who get SALT spectra and Mount Hopkins spectra. Because we had a pipeline in place from our high redshift pan-stars survey, we can immediately reduce the data. It's the same camera, it's the same data, everything's pretty much the same. The exposures are much shorter. These are 15-second exposures. And as a result, we get photometry within minutes. And the beautiful thing is, because pan-stars has already observed all of the sky visible from Hawaii, 3/4 of the entire sky, we already have templates. So we can do image subtraction immediately. We never need to worry about that. We have photometric calibration, already uber calibrated everything. So within minutes of observation, we have publication quality light curves, publication quality photometry, which means that we can move very quickly through the analysis. And so as of today, we have 82 supernovae. These are light curves of them. It's a mess because there are too many objects. You can see this is our test run. We did this first object. This is Assassin 15BM. We did this in twilight observations just to see if it would work. And it did. And so then we started. And you can even kind of see what we did. At first, we were doing longer exposures, 100-second exposures. That was overkill. We were worried that we're only paying for open shutter time. We're buying our time. We're buying open shutter time. We don't pay for overheads. And so we were worried that if we went down to shorter exposures, they would get upset at us. But it turns out that we can get down to 15 seconds without them yelling at us. and we're paying only for those 15 seconds. So each supernova all the way through the light curves ends up being like a couple $100s. It's very economical. So we were playing around with some things and trying some stuff out. You can kind of see how we ramped up. Not all of our data is actually on here because we require some cut. Today is like here. And we require some number of objects number of photometry points before we fit. This is a SASN 15SO. It's at 20-ish megaparsecs, very bright. And you can see the cadence that we've been getting with that one. And we're about to finish up a paper on this. We just have to go through a few quality control checks and things like that. But we're almost done with a paper on this. And we just started in April. This is our redshift distribution. Maybe I should have made this plot a little bit differently. But this is redshift 0.15, our low redshift limit. And then there are the couple objects that are in this nearby calibrator sample. And you can see that our sample is higher redshift typically than the low redshift sample that's being used currently. After all cuts, some of this can improve. Right now we have 68 supernovae. We're intentionally observing some weird objects that we wouldn't normally include on a Hubble diagram with the hope that one day they could be calibrated. We don't want to bias ourselves with that. There are also some objects where we don't actually have good redshifts for the host galaxies, and so there's a big redshift error, and that propagates into a large distance error. And like I said before, this is the second largest low redshift sample right now on a single system. And I'll get to the Hubble diagram in a minute, but I'll just point out these are, in blue are the good ones that we say, our Hubble residuals and then the Hubble pools. The pools are pretty much consistent with having the right errors, especially if you exclude these outliers. The residuals seem to be pretty good, but like I said, we're still dealing with some of the data quality, and we'll improve that. Here's our Hubble diagram. The blue points are good points. The white ones are something, typically what they are is they either have too few data points because we're just including everything right now, or they're spectroscopically peculiar, or potentially they have the wrong redshift. And we're getting through that. So your eye should focus on the blue points where, for the most part, things look okay. Our scatter is good. It's something like 0.12 to 0.14 magnitudes, which is better than any other survey right now, and we haven't even gone through all the quality control cuts. So this will hopefully get published relatively soon. And so I'll just show some predictions. These are just simulations, both low and high redshift, but just replacing the current low redshift sample with the high redshift sample. We think we can change this error on W from 0.05 to something like 0.04-ish. And if this works out, that's a 42% improvement in precision, just with that replacement, doing nothing with the high redshift sample or anything like that. Yeah?
Are you going to decide what to throw out before you have the whole data set, or after you have it?
We've already made those decisions. And so they were actually predetermined because they were what we used for the high redshift analysis years ago. We're just continuing with that.
Could you go back to this one? So we now believe there's the photometric error of 0 points is negligible, right?
Yes.
Remember the magnitude is smaller, something?
Yeah, I mean, we're talking about like a few millimags. Yeah.
Okay, so what's the scatter I'm looking at?
All right, so some of it is intrinsic scatter. We think that at least 0.1 magnitudes is intrinsic. And probably, 0.12 or 0.14, we're really bumping up against that. So almost all the scatter is intrinsic. This dotted line, this is your the error from the flows. And so we've corrected for that, but you could imagine that our errors in that correction are not perfect.
Is that a sigma on the flows? 1 sigma?
Yes. And so right, we did make these corrections, but they might still not be perfect. But those are the biggest errors for sure. And then there's some error in fitting the objects where maybe we've got a data point at maximum or a day after maximum, and so then things aren't as well constrained.
So now that you have this kind of accuracy, have you looked to see what the distribution function looks like? or the residuals? Are they,
Oh,
is it something Gaussian-like, or is it?
yeah. So, all right, sorry. Here are the residuals, and they're pretty Gaussian with the exception of these outliers. So I would say don't look too carefully at this because we're not done. But if you want to take something away from this, they look pretty Gaussian.
What are the
Those are in magnitudes. Yeah, there are some big outliers, right? So, there's like this guy. Okay, boy, there's not much time left. And I was going to talk about a whole different topic. Maybe I'll just briefly tell you something about WFIRST, which is scheduled to launch in about 8.5 years. And hopefully you know about this. This is the flagship mission from NASA for the 2020s. This is what's going to happen after JWST. And basically, it's got this giant near-infrared imager. It also has a GRISM. It's got an IFU, and it's got a coronagraph. And the major science goals are dark energy and planets. Dark energy through BAO, weak lensing, and supernovae. Planets through microlensing and these coronagraph observations. There's also a GEO program. And these science investigation teams were just announced. For BAO and weak lensing combined, it's run by Olivier Doré, and then Scott Gowdy is doing the microlensing. And then there are 2 teams for the coronagraph. There are also 5 GEO teams run by these people. And then for supernovae, there are 2 teams, one by me and one by Saul Perlmutter. For the dark energy, right, there are 3 total teams, one by Olivier, and then one by me and one by Saul. Olivier, of course, does 2 topics, and that's just indicative of how important supernovae are, right? There are 2 teams for one topic instead of 1 team for 2 topics. Anyway, so this is my team. My postdoc, Rebecca Hounsel and Dan Skolnick. They're kind of lifting a lot of heavy weight right now. Then there are a bunch of other people who are involved, some big names, but we were a really young team. I think the median age is probably around 32 or something. We're a young team. And briefly, in case you didn't know, WFIRST is planning on being essentially the telescope is going to be very similar to Hubble because there were these spy satellites that were just sitting in some warehouse, and then eventually the spy agency said, we have better spy satellites sitting in warehouses, so here you go. And they
That's actually not true, right? The program got canceled.
Oh, the program got canceled.
I think it was because
They probably have better ones too, right?
They better.
I've heard it said that they don't have anything larger than the 2.5 meter.
Really? Okay.
Waiting to see what JWST does.
Well,
They probably don't tell us the truth.
regardless, NASA now has some new Hubble clones, and so this is going to be one of these is going to be used for WFIRST. The imager is enormous, so this gives you a scaling of sort of how things look. This is a single image if you were to plot it out at full resolution on the wall relative to some cartoon people, and really the numbers you probably want is it's 200 times larger than the field of view of Hubble, but at Hubble resolution. Here's a simulated image of WFIRST compared to Euclid. WFIRST is going to do a lot better than Euclid for some of these different science goals. Here's another way to look at the image. Here's the WFIRST field of view compared to different Hubble and JWST field of views. So I'm interested in the dark energy component of WFIRST, not so much the planets. And there's this very complicated path to getting to dark energy science. But the one thing I wanted you to take away from this NASA-generated flowchart is that there is one survey that does the weak lensing in BAO, and there is a separate survey that does supernovae, that they really act independently. And there was a science definition team that went and made a case, a strategy for the supernova observations, and I'll try to be nice about it. It's very complicated. And it requires real-time decisions because what they do is they find supernovae in broadband imaging using that giant imager. But then they use this tiny IFU to follow them up. and they use the IFU spectrophotometry to build up light curves. And they completely exclude the images from any of their measurements other than the discovery. And so you have to choose, one, what objects to follow, which means determining when they're young and if they're a 1A. And so this is the plan, is to do this thing. And the spectra are kind of funny, too. These are the light curves that you might reconstruct. And down here are sort of these epochs of how you do this. And there are 3 different exposure times that they call like these typical or nominal exposures that are supposed to be signal to noise of 3.5, but they're really signal to noise of 1.4. And then they have a classification epoch, which is this one here, this second epoch, where they get a slightly higher signal to noise spectrum, which was supposed to be 6, but it's really 4. And then they have a deep spectrum that's supposed to be at maximum, that's supposed to be 10, but it's really 6.5. And a lot of the reason why these signal to noises are off, well, there are 2. One is the way they actually made these numbers was they said, if you had a typical 1A and you measured the spectrum at maximum, what would the signal to noise be? But in reality, a lot of times you're way down here. And so your signal to noise is just going to be lower because your flux is lower. But the other problem is that with an IFU, you still need to do some sort of template subtraction. It's on top of a galaxy. You need to remove that. You're trying to do spectrophotometry. You're not just trying to get a redshift. And if you do that, you need some sort of observation out here, which they only put out at this classification depth. So signal to noise of 6. And you know what happens when you take a signal to noise of 10 observation and you subtract off a signal to noise of 6 observation. That's why you have signal to noise of 6.5 for that. So that's a big error that they haven't accounted for. And you can even see these are supposed to be these galaxy observations. There's scatter in there that they just didn't include in these light curves at all. And that's a big problem. And there's a lot of other questions about repeatability of the IFU and things like that. But one of the other things that we had to do is you actually have to classify these objects because you have to follow them up one by one. And maybe I'll show just 1 or 2 of these. So this is a signal to noise 3 spectrum, that first epoch that you would get. They're not trying to classify anything. The gold here is a 1A template, and the red is a core class template. And what you can hopefully see is that the spectrum is really noisy, and that both templates are pretty consistent. But you can do color cuts based on the photometry. You can look at the spectra and try to make some other cuts. And you say you follow this one up. You can get a slightly higher signal to noise. This is this second spectrum, the classification spectrum. And here you would say that it looks like a 1A template, mainly because of the difference here. Of course, in reality, this is without any galaxy contamination. And when you're doing this in real time, there's going to be galaxy added to this at some level that's probably unknown. And so the actual shape here might not be very well constrained. In any case, you say, all right, that looks more like a 1A, we'll continue. And then you get this really high signal to noise spectrum later. And here you can maybe say that this actually is a 1A. And if you go by the classification scheme, we simulated this fully. You would say this is a 1A, this passes, you follow this completely. But you can do the same thing again. Here's another one. I'll go through these same epochs. And here, this is a 1A that was classified as a core collapse supernova. And so you would just lose it. That's not the worst thing. The worst thing is here, where this is a core collapse object that gets classified as a 1A. So you would follow that up. And so as a result of this, they have some sort of redshift distribution that they want, but you're not going to get it. One, the main thing is that the area is actually not large enough at low redshift to find enough supernovae to get their intended redshift distribution. But then their follow-up is also not very good.
Can you turn those into synthetic phenomena?
That's what they're doing, right?
As opposed to, well,
So, right, so this is true spectrophotometry in the sense that with the IFU, you supposedly get all of the light.
can't you turn it into broadband?
That's right. So if I go all the way back,
No, sorry.
sorry, no, it's fine.
Well, that is.
That's what they're doing here. Of course, they didn't actually, right, so I should point out, so this STT team and report, they didn't actually simulate anything. They didn't simulate, they didn't take spectra and then actually synthesize the photometry. We did that, but they didn't. Okay, I know I'm running over. So
That's Saul's proposal,
that's Saul's proposal.
but then there's yours.
Yeah, so we fully simulated everything. We fully simulated everything, including systematics. They assumed systematics. We've done it all. We've made all the Hubble diagrams. We did the contours, did the figure of merit. We do really, so this is doing Saul's proposal. And I'll just quickly point out some synergy here. The final WFIRST figure of merit really strongly depends on the number of low-redshift supernovae that you have. WFIRST wants to have a low-redshift sample exterior to it, but you could imagine this being Foundation, and having 200 objects is great, but 800 would be better. That switch is an 80% improvement in the precision for the figure of merit. So we tried a bunch of different strategies, and we're not confident that we know the most optimal strategy. But what I am confident about is that there are strategies better than what has already been presented. So we looked at things where we only did imaging, or we only did the IFU at low redshift, or we said, what if the IFU broke on day one? Right? What would happen? And you just use the images that they have. And so we could compare the figure of merit. We varied the different systematics from some current value to an optimistic value. This STT report is similar to our optimistic value, a little bit higher. You can look at the statistics only. So this is what happens if the IFU breaks. This is what happens when you only look at low redshift. And this is what you do with only an imaging survey. And only an imaging survey does significantly better than the IFU survey. It's much easier, of course, because you don't have to make those same real-time decisions. You just image everything, and after the fact, you classify things. Maybe you want to get spectra from the ground, and you could do that, right? That's not too hard if you just buy Gemini for a couple of years, which is cheap. This is $1 billion experiment. It's cheap.
Brian, let me understand this. I mean, you're not saying there's something missing from the WFIRST, the way it's configured by the SDT. You're saying that the IFU you think is not the way to do it.
Well,
or is there something missing?
Well, all right. So I would say one, if you want to do an imaging only survey, if you had a bluer filter, something like VRI, one of those, you'd do significantly better. And the other thing I would say is that the IFU might be very useful, but my guess is that the more useful thing is using the GRISM. If you want spectra of the supernova, you can use the GRISM in multiplex. And you can get of order 5 to 10 times as many objects with spectra and full spectral sequences if you wanted to.
Testing, right?
Yeah. So I know, and I'm late to the game here.
I think, I've never been through one of these things completely, so I don't know. I assume that NASA has picked you guys as two teams, partly to fight it out, and maybe to do both, maybe to do one and not the other. But the SDT was just a way of
That's right.
trying to get the possibilities.
That's right. And I think,
Up to you now.
I know, so the key here is, one, we fully simulated this. So we're not making any assumption, well, we're making assumptions, but we're not going wild with our assumptions. We make our assumptions and then we fully simulate everything. We go all the way through end to end. And so you can make these comparisons in an honest way. And so we're not done though, because what we did for the imaging, we just took the SCT imaging where they had these 3 different layered surveys and we just multiplied until we filled up all the time. And that redshift distribution is probably not optimal. We haven't really decided what the true systematics are of the IFU versus the systematics that you would get from supernova physics. And if you think it's supernova physics that's going to dominate at the end of the day, you want numbers. So you can say, let's look at everything in an elliptical versus everything in a spiral. Let's look at everything with a broad light curve, with everything with a narrow light curve, all those things. You want to do all those things, and the more numbers you have, the better. Now, I'm really, I don't have time, but I will say, if you want to, we also have a public website. You can download all of our code, run everything, get the same results, change whatever you want. So feel free to do that if you want. I don't know if you will, but. And then I'll just conclude, and I'm sorry for taking up so much time. And I should just say that we really are continuing. Supernovae are not old hat. They continue to be the best, and they're the best tested. They're really the oldest, best known probes for dark energy. This Foundation Survey will soon make this calibration systematic subdominant, and then we have to find out what the next thing to hammer away at. It's probably dust. WFIRST is happening. There's $90 million in the congressional budget for it this year. If you're not already thinking about it, you should. I know some people in the room are on one of those groups that flashed by. It's a long ways away, but get ready for it. That's going to be the flagship mission, right? And the way that we think of Hubble today is what we will think of WFIRST a decade from now. This Supernova Survey, it has a lot of potential. We just need to figure that out. And so if you have suggestions, please let me know. We only have about a year to figure out the strategy before things are set in stone. And I'll just stop there. Thank you.
Okay, so any questions? Go ahead.
Ryan, can you give like a very brief summary for someone who typically thinks about stars of exactly what the linear scale of the dark energy figure of merit is measuring?
Yeah. Oh, sorry. I probably should have at some point actually said what the figure of merit is. So the figure of merit is the inverse area of the 95% contours in WWA plane. Okay, so in some sense, it's the precision at which you're measuring dark energy with these two parameters. So larger figure of merit is better, and you can, it's not necessarily the best thing because you could imagine something that's very narrow in one parameter and large in another, right? And that's not necessarily your ideal situation. It would rule out some models, but then there might be other models that are completely different. So there are a lot of ways to parameterize it and a lot of ways to compare these models. That's something that we're actually looking into because you could imagine two strategies having similar figure merits in this way, but then when you say, I want to look at modified gravity or something like that, it might be completely different where one is much, much better. In the same sense, when we're talking about these different surveys, what I can say for sure is that when you use the IFU for 75% of your supernova time, you're really only getting supernova data. If you're imaging for that time, there's a lot of data for other people. I could imagine a lot of people wanting, hundreds of observations of these fields for, something like 100 square degrees or maybe a little bit more. So, again, can you take a slight cut on your figure of merit to really satisfy the broader science goals of the community? Those are things that are above my pay grade, but I can make suggestions to NASA for those decisions.
I'll put you on the spot here. 4% cosmological constant, consistent with 4%. And I think I agree with you that too soon to stop. Where would you stop?
So people ask me this all the time, and
We're recording.
yeah, I know. So there are different ways to look at this. The practical way is you keep doing it until it's no longer easy, right? So there's some point where instead of $1 billion mission, you need a $100 billion mission, those sorts of things. And obviously, you just don't do that. There's the scientific thing, though, which is probably what most people really care about. And there, I think it really depends on what the answer is in the next few years. If we continue to go to cosmological constant after, say, WFIRST, which, really, by the time WFIRST is done, that's 15 years from now. If it really is at that point where we really look like we're cosmological constant with the constraints that WFIRST and LSST are going to give us, I don't know. I'd have to, based on the current theory and based on those constraints, I would say that it would be difficult to make a substantial, order of magnitude difference within a decade. And at that point, you say, maybe we put this on the shelf. But of course, you can always look at something like the Hubble constant, which, of course, here everybody's well aware of. There are reasons to go from 3 or 5% precision down to 1 or 2% precision that go beyond cosmology. And the same goes for dark energy. If we really know what's happening at redshift 6 with dark energy relative to what's happening at redshift 2, redshift 1, and maybe even going forward, that can tell us a lot about, galaxy formation, structure formation, and I haven't gotten a clear answer from people in those communities saying what precision they need to enable their science. Obviously, if you just if you ignored lambda and you tried to build a universe, things would be wrong. All the structure would be wrong. And so clearly, lambda equals 0 is not good. And the question is lambda of 0.7 and W of -1 good? Or
Well, I have to take issue with you there. I mean, lambda was insignificant back when galaxies would be born. So
sure, but the structure we see today was definitely influenced by dark energy, by the acceleration.
But isn't it sort of really make itself felt at that redshift?
Right, so it's a question of where you are. So if you're saying,
Redshift 6.
well, right. So, but we don't know what's going on with dark energy at redshift 6. We think we have an idea based on things like galaxies, but we haven't had a direct measurement at all, right?
Right.
And so I would say you're right. The likelihood of that being important is probably very small, but we might want to measure that at some point. More importantly, though, I think is just seeing that full evolution and where it all goes.
Yeah, so right. So I understand that when we do foundation, you greatly improve the measurements of W0.
Yeah.
To that by 40% with only 60 or 70 supernova. But
Well, the 200, that's the projected, yeah.
Yeah, but for WFIRST, you will find a lot of high ratio supernova. But how do this supernova add to the precision of cosmology?
Yeah, so, all right, so perhaps this is the best thing. So our figure of merit right now is like down here. And so this is supernovae.
When you say our figure of merit, you mean that
What we know about dark energy right now. What we know about dark energy right now, is down here. And so this is supernovae plus CMB plus BAO. But it's using today's CMB, today BAO. So there's some way of just saying, all right, you were here, and then the supernovae give you this. That's sort of the way to think about it, but it's not exactly right. Because if you had decade from now CMB, decade from now BAO, then things will be a little bit different. But the supernovae definitely improve things. That's what I can say. One is that you're going up an order of magnitude or so in your precision. The other thing is that for WFIRST, all projections say that the supernovae are going to give significantly better constraints on dark energy than the other components. And that's even ignoring Euclid, where Euclid will get a good amount of BAO information. And so when you compare Euclid BAO to WFIRST BAO, they are kind of comparable. But if you compare WFIRST supernovae to Euclid supernovae, which doesn't exist, it's a very good comparison for WFIRST. So does that sort of answer your question?
Yeah, well, let's say that for the figure of merit,
Mm-hmm.
so we are not down there.
Yes.
Let's say after you down foundation,
Mm-hmm.
where would be?
Well, so after foundation, I think the number that we were saying is like we'll be at like 150, somewhere around here.
And after WFIRST,
And after WFIRST, you choose your poison, but somewhere, well, so this is, again, when you add in the decade from now BAO or 15-year from now BAO and all that stuff, I don't know, we'll probably be somewhere in this range when you add everything together. And I'm sure that, in the next decade, somebody smart will come up, right? Like if you go back 20 years, nobody was thinking about BAO, right? They were thinking about structure and finding omega matter and stuff, but they weren't thinking of the same kind of things. And so I'm sure you go a decade from now, somebody smart will come up with a really great idea. And so it's always hard to predict these things. But if I were pressed, I would say in 2030 we'll be somewhere in this range.
All right, well, let's thank Ryan again. We'll be going to dinner, so if you're interested in joining us this meeting.